Yeah, it's time for the first technical speech. It's given by Richard Rodell. Richard has been in test engineering since 33 years, working in multiple roles, from development of VP of test engineering, and he has worked on a wide range of products from memories, complex SOCs, advanced analog, and RF. He has a long experience, and I will leave the floor to Richard to give his talk. And yeah, I hope you will enjoy.
Thank you. Good morning, everyone. I'd just like to say it's an honor and privilege to present to you today. I hope to show you something that I've been working on personally for probably 15 years to basically drive this together. So what we're going to talk today about is the test development ecosystem. So an ecosystem, is fundamentally an entire tool, an entire environment of tools, technologies, practices, and communities that support a creation, deployment, and maintenance of a system. In many ways, if we compare a test development environment to, a biologic ecosystem, we see a lot of similarities in that, the parts are interconnected. You can't have a standalone tool. It's the connection of tools. These tools evolve together. New frameworks rise, and the old ones die out. And that's really what we're going through now, is a much faster evolution of this framework than we've seen historically. And they adapt to external forces, whether it's climate change. In our world, we're kind of going through a climate change event right now with regards to AI and how we think about our jobs, how we think about what we do every day. And then there's a large amount of balance and compatibility. You can't rely entirely on one system. For the sake of this presentation, I'm going to talk about the test solution as a whole. And this really starts from silicon, the design, the DFT insertion to that design, the hardware development, the test program creation, even integration with the handlers and the probers and the sockets. It's the entire test solution that we have to look at during the development process. And so today I'm going to look at the evolution of the system and I'll look into the future. So when I started as a test engineer, a lot of you, at least the older people, would recognize some of these systems. And my first chip, I was the test engineer, I was the product engineer. And, my world basically revolved around an oscilloscope and a CRT. And, the programming languages were very, antiquated. This was 30 years ago. And everything was single site. It was a very, very, call it simple problem. If I fast forward 15 years, this is when we really started to drive into, say, complex SOCs, at least in my company. And the average test program had at least 5 test engineers. We started going into the world of offline and online development, where we could basically emulate, simulate, build offline. ATPG was something that was like standard by this time. And we really got into, standard revision control. It was sort of interesting. At my company, we didn't introduce like Subversion or ClearCase until, 2007. And so, revision control at that time was still just file naming conventions, RIC 1, RIC 2, RIC 3. And it was like you couldn't figure out what you'd done. And, with the introduction of the, Nextest Magnum here, we finally got into like C++ programming, which allowed us to go into like an object-oriented approach to how we program. And probably the biggest change was how we were able to execute on debug. We finally had the ability to VNC into our systems, either locally onto the sort floor or into another location geographically. And from a debug perspective, we were able to see things via this virtual window Whereas historically, everything was with an oscilloscope, everything was very hands-on to figure out how it worked together. Now in 2025, things have advanced much further yet. As now we're seeing, at least 10 engineers on every chip, in some cases as many as 100. We still have 100% online and offline development, but we're basically seeing continuous advancements in ATPG. We've heard a lot about that, in the conference and how patterns are growing and complexities changing. And we're getting more advanced DFT techniques, which basically are allowing us to see inside the chip better. We're also seeing that style and protocol aware are becoming sort of de facto pattern languages so that it's much easier for us to interact with our testers. We have advanced revision control, and what I mean here is we basically are running multiple branches. We're branching and merging, and it's very advanced in terms of when you branch, when you merge, how this stuff fits together. And we see fundamentally the emergence of two programming languages that are dominating our test development world, and that being Java and .NET. And of course, everybody has a very strong understanding of Python, and so the jump to these two languages is very natural. And probably the biggest step forward that we're really driving is, adopting to a CI/CD flow. And that is, we need to do continuous integration and continuous development deployment. And we're seeing tools like, Jenkins is old, it works, but we're moving into things like GitLab, where it basically gives you a much better environment with like GitLab Backstage, GitLab Duo, and other tools that are available, from third-party companies. And we're seeing that the IDEs are truly getting to be a true development environment. And so through the IDE, you can fundamentally see what's happening. You can see your instruments, you can see your flow, you can see your sequences, you can see your test time, you can see all this stuff. Whereas before, it wasn't native. And finally, we're getting integration of our first generative or helpful AIs with the integration of Copilot into our IDEs. And that gives us a lot of benefits. And it's very interesting if you started using it, how much it knows, because our test programs, by definition, have a lot of context that can be linked. So as we go into this digital transformation, we see this, in the last 20 years, a big transformation. But just to kind of zero in on to like the 2030, 5 years from now, can we get to like sort of fully autonomous testing systems where it's basically looking at the results and dynamically feeding back into the system to basically, toggle those results, change those results. We're seeing AI-driven, and something I'll get into a little bit more of here, predictive real-time insights. And so as we're drilling into this, how do we think about what do I look at next? How do I generate that first level of Pareto at first silicon to see what do I go work on? And the other thing is we're seeing is much more advanced digital twins. And a digital twin is fundamentally that correlation between online and offline development. We're driving more and more so the offline environments and the offline results emulation is much better than it was long ago, and it continues to grow there. So how do we get simulations to match silicon? How do we get the test program to be emulatable? Things like that. So the storyline for test engineering in Infineon, and I think it's true for the industry as well, is where are we? Each test engineering organization has their own custom test development environment. Methodologies in those revolve around their perceived needs. You always hear, well, I'm doing FinFET, well, I'm doing a PowerMOS, I'm doing this, I'm doing that. And so they drive around those. And what we see is some groups, like our automotive group at Infineon, has expansive frameworks, while in other groups it's still ad hoc. Think of even pre-2010 where I showed it there. A single test engineer, limited debug, etc. And fundamentally, we've hit a roadblock where unless we harmonize this tooling, methodologies, and framework, we're not going to hit our productivity requirements. It's just not going to happen. And so how do we get there? So what I'm doing is we're defining a framework that's deterministic and to a certain level tester agnostic. There's a lot of things that we do that are not tester ATE dependent, but they are very specific at the implementation level. And so I don't want to basically say you can test anything anywhere. Of course, that's a complete falsity. And we want to develop tooling around the software industry's best practices. The software industry is moving at light speed, even faster than, every 6 months. I thought I knew what was going to happen, and 6 months happened, and I was wrong. And so we need to basically get into a fast follower mode with the software industry as we develop our test programs so that we can learn and adapt as quickly as they do. We're using a protocol for universal test specifications. Right now, I'm grabbing all the information from all my designers and porting them to something like JSON, which in .NET and Java and Python, you can read JSON in one line. And then using a universal pattern language, whether it's style or protocol aware, and basically abstracting that away from how the tester's implementing that to make sure that we have clear understanding. And then we're structuring our test methodology with a real focus on reuse. My question to every one of the test engineers that's ever worked for me is, why are you developing that? Why aren't you using something copy exact? And we see a lot of challenges with copy modify. And everybody's doing copy modify, and it's like, why don't we just copy exact? And so again, we need to get to that point, and we've proven that on platform products where you have 15 die running the same technology with different combinations of IP. And lastly, we want to automate the test program generation. And it's not, to be very clear, this isn't generating a perfect test program. It's not even close. But what it's doing is it's creating an environment, it's creating that ecosystem that allows us to get a test program that's functional, that works, that builds, and then we can get to work. Our engineers spend too much time, and you guys spend too much time fighting with the test program. You want to fight with the silicon. And so where do we want to be? Fundamentally, we look at that above, and I'll go through this in the next pages, and develop an architecture around that. We want a universal test specification that's digestible by AI tooling. What I mean by that is it's presented in a format that AI can easily create the tokens and link the tokens together between specifications and yield, specifications and this and that. And we actually have that nodal analysis already done in our industry because everything is natively linked. If it's not, there's something wrong with your test program. And then we want multi-platform portability and a certain level of test commoditization. And it doesn't mean, instantaneously platform A to platform B, but it allows us to see what is the benefit of going from current generation to next generation tester quickly. And understanding how is that going to create productivity across all of those aspects. And lastly, I think we need to synergize across the test engineering organizations within our companies, but also as an industry, understand how do we basically build a system that's basically going to allow us as an industry to move forward. So we developed something called United. It's just an acronym. But what we see here is kind of some components that build our test program together. I'm not going to go into all the details, but the test package lifecycle management is really how do we go from first silicon, pre-silicon, to mass production and understand how that lifecycle happens, from generating our test program to doing offline simulation and debug, to doing online debug, to optimization and through. Understanding what our universal test spec looks like and where it resides. At my previous company, Cypress, before we were acquired, we tried to extract this information from paper. They're electronic specs, but they weren't in a database. It was a complete disaster. Now we're basically driving all of the specs using a requirements-driven design flow to basically have those specs in a queryable database. We need a pattern management platform. Patterns continue to evolve, optimize, change very dynamically. And we need to be able to manage the patterns such that we can understand how they're evolving over time in coverage, in space, in test time, in creation, conversion, integration. And lastly, from a test package bill of materials, this is really about, like, as I go through this development, how do I create all of the appropriate artifacts so that I can learn? You know, many times as we develop our test programs and then we go to learn, generate learning feedback, it's very challenging for us to find cause and effect just using memory. And so my hope is that as we grab all of this data, we can actually ask our AI partners to summarize this information and get us to a level where we can then talk as people and figure out what the most impactful things were. And as I mentioned, the key here is that we evolve around a software industry approach. And so I just threw in some tools and names. I think the most important area is really how do we generate reuse, regression, and control in that area. But on the other side, it's like in the lifecycle management, we're using things like low code and Tableau to generate dashboards and visualization. We're using pattern management tools and conversion tools, both internally developed and using vendor tooling. And we're basically generating through our program release and regression cycles this test package bill of materials, and that's going into an Infineon test data lake. And that's a combination of data sources. So as I mentioned, the most important thing that I see is establishing regression flows that are both standardized, scalable, and they do call it the work functions that we need it to do. And so generically, the regression stages are, from left to right here. Basically, you have your source code management, all your different block repos, your shared libraries, all your specs and everything. And then you're going to build and audit that test program. In my world, this is really about configuring the test program and then aligning, the flow and the configuration of that. So the automated test program generation is not code generation. It's generating, an IG workbook. It's generating a .flow file. It's generating a .spec file. And the code itself is still sitting in your test methods and your test instances and whatever you write there. And we build and we load and we audit that program. And when we audit that program, we use things like SonarQube or Spot Bugs or something even customizable that allows us to grab information from that process. We then run the test program offline, online, and again, we have multi-branch, so we can run different operating systems, we can run different targeted flows if we're just targeting our scan DFT flow versus targeting the whole flow. And then we analyze those results, and we basically look at those. We've done a lot of work on like Q-score creation, which is looking at repeatability, test time targets, and basically trying to adapt to where it basically gives you a good representation of is this test good or not, and then the sum of those, is this test program good? And in this analyzed results, we're also trying to quantize and quantify the coverage. And lastly is we archive this information at the end of each of our regression so that we can basically see in time, how are things progressing? Where are things progressing? And what we've seen on like our platform designs is that there's a lot of static code and static portions of the test flow. And then there's these other portions of the test flow that are incredibly dynamic. The scan bring up, the non-volatile memory debug and bring up. A lot of those things, you see a lot of churn there. And so in this archive, we can basically go back in time and basically say, why are you touching the ADC test? This has been released. Why isn't it working? And so it gives us the ability to look into that. And so now as we look into, the future of how we can interact with this ecosystem, is historically, and even today, we had tens of different tools, and none of them were tightly coupled. And at Infineon, there are tools upon tools upon tools within the business units, and they never even talk to each other. And so there's very limited connections there. And then in the last 5 years, we've seen a much better self-service sort of portal solution where you can go get work done. The easiest one for companies and stuff are just all the HR portals. But we don't really have test engineering portals, like, oh, I need something new, please deliver this to me. And we've played around with that. But what we're seeing now is really moving into the area of like orchestrator AIs. And you can think of an orchestrator AI where it's basically functionally interacting with all the pieces to basically create your ecosystem. So you could sit down at your system as a program manager, as a lead test engineer, and basically say, I want to create, a new test program, create a new ecosystem for this product, use this product as my reference, this and that. And the orchestrator will go out and it'll set up a GitLab regression. It'll import and set up your SVN externals or your submodule linkage into whatever things you need. It'll create other content that you've enabled through this orchestration. And it'll basically get you to a point where you can be a functional test engineer, in a day. And that's really where things are moving, and we can see this orchestrator AI happening in other areas. If we think of where we are with agentic AI and with orchestrator of these agentic AIs, is we basically see that agentic LLMs are like a new operating system. They're not like a standalone tool. It's like, this is the operating system that we work within. And you can see this from a Google perspective and how you have all of these interconnected operating systems running through Gemini that allow you access to photos and email and a calendar and this and that. And this is really where, as we think of this, it's like, how do we get to a level where we basically have a pseudo-agentic ecosystem? And so a solution that's come out recently, in the last 18 months, and it's gotten a lot of traction, and since it's in the AI space, in 6 months it'll probably be gone, but there'll be something very similar to it. And that's something called the Model Context Protocol. And the analogy that they've given a lot is this is like the USB Type-C for AI. It's designed to provide more deterministic interactions. So like if you're talking to an EDA tool, it doesn't care about these topics. If you're talking to the tester, it's really thinking about the tester. And what we see is this MCP is a standard interface that allows the AI models to connect to external tools and services dynamically and intelligently. And so just like on the right side there, it's like, what can we plug into our system? And what do we point that to in terms of LLMs to get the best performance? And then downstream from that, how does that link up? And so an MCP server is really listening to requests from the MCP client. And so the MCP client is anything like your IDE, like Copilot, Claude, self-delivered tools. And it's basically providing a service. And so basically the MCP server is looking for like a prompt template. Like it's looking for key things that are going to come into it. And based on those key things, it's basically going to access the data, the file system, the database, things that you want it to. And then it even gives the ability to provide a function and return back a higher level answer. And so this allows us to basically have MCP servers that are supported by our vendors, like the EDA vendors, the ATE vendors, and then also local MCP servers that allow us to talk to our yield information, talk to our design information, talk to our register maps, and things of that nature. And the other thing MCP brings, and this is kind of a point of contention, is you can actually have an MCP server serving something off-prem. And they have some things in place that allow us to have secure protocols over this. And this is really where I think it's evolving, is how do we differentiate and how do we drive on-prem versus off-prem learning? Because if you're sending context, you're sending data. And in all honesty, the Copilot doesn't care what it sends, it just sends it all. And then it's looking for a return, and then it kind of summarizes that, and then it sends it back, and it keeps doing that until it converges. And so you don't really know what's going, and you can put a sniffer on there and watch it, and it's amazing the amount of information that it sends and how many tokens are going. But it basically gives you this ability to structure this. So in the test ecosystem, at the top are ideas of possible MCP servers. We have all of these things, and these connections basically enable the ecosystem. And the ecosystem drives the structure of this data. How do we capture this data, put it in a place, where the MCP server is actually looking at it? And then the structure ensures scalability. In the beginning, like with everything, we start with one simple server, and then we basically figure out, as a company introduces a server, as another group within Infineon introduces a server, how do we generate that connection? And then down below are just sort of some ideas of what am I looking for from an insight perspective? So yield improvements. You're looking at the absolute yield, of course. You're looking at your test program. You're looking at the ATE. You're looking at the design. You're looking at the characterization data. And very quickly, by pulling all these things together, you should get some insight that basically says, the characterization data showed this number. Your data is showing this number. And so the future of AI isn't about better models. In all honesty, we've seen the models that exist today are as good as the data. We haven't had a model problem, we've had data problems. And the models are only getting better. And so for us, it's really about how do we create this data capture and this ecosystem that allows us to then prompt the right information. So, what is the new normal? Historically, we always had, product engineering, test engineering, characterization engineering. Depending on the company or the organization, there's always overlap and things like that. But, in the future, it's can we connect these things into one sort of source so that we can get this information more tightly coupled and derive those critical insights from that information? And I think the answer is yes. The test engineer is still responsible for the test program, for creating the information, for understanding what the coverage is, understanding all of that thing. But more importantly, they're also required now to create the data that can then be shared via these connections. The other new normal is sort of these vertical use cases. On the bottom right there, I think every engineer in this room has been here, right? The silicon, the design engineer says it's a yield problem. The product engineer says it's a test program problem. The test engineer says it's a design problem. And so you continuously have these cycles of learning. Well, give me a new pattern. Well, it still fails. Do this. Well, it still fails. And what we see here is, especially when we get into platform design, it's like the design engineer can actually go in and say, how is my SAR ADC performing across all of the designs it's been implemented in? And it could pull all that information for the design engineer and give them that first level Pareto, and then they could basically drill down into it. For reliability, you get a customer return. You can ask the system here's the data log of the failing part. What happened during the test program development that is in relation to this specific failure mode now? And it could basically look into that revision history, look into the artifacts that we've saved and basically say, the voltage was changed on the MBIST, hot temp insert, blah, blah, blah. And from there, it basically could give some insight and get that first layer of communication happening so that as the customer return came to the product engineer, came to the test engineer, they would have a much more insightful starting point. And this extends across multiple areas, whether it's firmware, system validation, et cetera, et cetera. So I just wanted to give you kind of a real-world example that one of my engineers did here. And he literally just took an STDF data file, just a random one. It could be one that you have on your laptop today. And what he did is he just created a couple of MCP calls and environments. And so what he did first was he basically took and he ran a script that basically created an STDF kind of pre-processing that creates sort of the token environment of the STDF. He then ran a clustering scheme that basically, what it does is it links all the things together from a tokenization perspective. And then he summarized all the failures. And then what we did is we took the .flow file from the 93K program that this was run against, and we ran it through a program called Neo4j. And what it's doing there is it's creating for the test suite, it basically knows here's the test name, here's the conditions that were in the test program, and that information in there. And then he just ran it into our MCP client, the GPT for IFX, our internal node, and had it create an HTML report. And I have the full report, but I just thought I'd show you like some overview things. It's like, okay, it says, this was the session, this was our test time, and then from the critical insights, it basically looks into a test name and it gleams some information in terms of like site variability or this or that. And what's interesting here is this was a complete blind, so it didn't know anything. So in our regression flow, we could easily take every STDF file that's ever created and create something like this, which then is digested again by AI to basically summarize trends. And so this takes seconds to run, and it took a massive STDF file and basically found some site-related issues associated with a specific test. And if we had more information feeding in here, like the design, the test procedure, something, it might even be able to give us insight into, what the characterization data was, what this was, what that was, what's the CPK. If we had access to the yield information, we could see, is this a trend or something new? But again, the goal of this is not to give answers. It's to zero in on what to look at. And so I was in the panel yesterday with Miss ChatGPT-5, and I thought it was quite funny. But a lot of the questions we asked her, I fully didn't expect it to answer correctly, and it didn't. But if you asked it questions about data sets and how data sets are connected to each other, it does a very good job. And so you have to be careful as to what you're asking AI to do. It's never going to be, it's artificial intelligence, it's not intelligence. And I think yesterday we were asking it intelligence questions, and it didn't have all of the information to be intelligent. So going back into our overall test development ecosystem, as we basically see some of the tools and attributes associated with these different pillars. And I think, when we look at the universal test spec, especially in this day and age, is everything is IP, chip, platform, technology drift specific, right? And so how do we have universal test specs that allow us to look at the commonality across all of those things and make sure we have sharing? We see a huge amount of pattern management, whether it's protocol aware and register settings, making sure that we're using the correct register settings across an entire family. And then SSN brings in a whole another element of how is the test time progressing versus the coverage, and is there any sort of patterns in there that we can't see through the data. And I think the most important thing, and what I'm driving to first and foremost, and we actually just got it running 3 weeks ago, is really the use of regression in a structured, deterministic manner. And this allows us to basically create dashboards with these things like Q-scores. It allows us to get automated insights into not only the regression itself, but the data created by the regression. And it allows us to create more linkages in the regression flow. So on the first few pages, I put together like 4. It's actually coming up here. There's 4 boxes here. Depending on the chip, depending on the company, depending on the tools available, this pipeline could be, 20 stages, or it could be just a few. And down below here, we basically see, we're generating the test program, we're building the test program statistics, we're auditing the source code and reading that back. We're looking at test times, we're scoring results and highlighting problems and insights and successes. And archiving, we're building a history. And the other thing that I think we all do well as engineers and we focus on is, root cause corrective action. How do we get to true RCCA when we have so much churn and so much, so many inputs? And that archiving also leads us to best practices. As we look at a new chip, it's like, what is new from a test program perspective? Is the test program actually exactly the same, just different patterns? Or is there something fundamentally new? Or is it really a challenge about hardware, and the actual hardware creation to deliver that power? And so it really allows us to drive to best practices and make sure that we use what's working and only enhance, modify what isn't. So going back to this ecosystem view with the MCPs, it's really creating deterministic communications between critical areas. And that deterministic is really important. You need to have the ability to narrow what questions are allowed to be answered by which servers. Prompt driven by standard use cases. Prompt engineering is a big thing, and we need to understand when I ask a question and I get the wrong answer, what is the fundamental reason for that wrong answer? And I think as test engineers, AI didn't exist in this form. And so I actually asked, we had a speaker from Google, and I asked him, how did your team use Gemini from day 0 until today? And his answer was perfect. He basically said necessity. And I'm like, well, what did you do if it gave you wrong answers? He's like, we learned how to train it to give us the right answers. And he's like, and that's just this continuous feedback loop. And then we're using standard LLMs to create insight. We don't see the need to create LLMs. There is cases, I think, especially in, call it the vendor space, like an EDA tool, they may want custom LLMs that are basically targeting very specific things and how it's presented to those within their small database. But in terms of at my level, at the Infineon level, we don't need custom LLMs. So again, the future of AI isn't about better models, it's about the connections. So in summary, the ecosystem for me is really a basement and a foundation for test development. When I talk to vendors, when I talk to engineers, when I talk to designers, it gives me the ability to ask them, like, well, where in your development process did it break? Where did this data come from? What were the expectations at that stage? So it turns into like the way we work. And it also helps us communicate what we're working on, like what's working, what's not working. It's how we do analysis and form and drive learning. And so it basically allows us to plug things in. In the beginning, maybe there's just one MCP server. And in 10 years, we might have the equivalent of 50 MCP servers. And then the ecosystem captures that data to drive the future. It's really about how do we capture that data, because odds are this whole ecosystem is going to blow up in a year, and we're going to have to do something different. But if we've actually captured the data via this ecosystem, we can then basically say my framework definition that I just shared with you was wrong. And what are we going to do differently? Well, we've got all the data. Let's overlay this onto that data and see what happens. And I think the new normal is really about driving convergence of skills and getting better alignment to questions. You know, what is the problem? And sometimes the problem that we have is defining the problem. It's not actually, you know, solving the problem. It's like we can't really define exactly what the problem is. And then once we all agree on the problem, then we can start working on it. And I think part of that comes from like the design engineer is thinking like a design engineer, the reliability engineer is thinking like the reliability engineer. Us test engineers are very smart, so we know exactly what's right. And so it's going to converge this. And so why do we want to do this? You know, productivity is king. We saw in the first couple pages that it went from 1 test engineer to 5 test engineers to 10 test engineers. Eventually, that has to roll down to the point where we can orchestrate our test program and we can orchestrate the data with less people, and we don't have to write code because the code is generated. We don't have to write the test program because the test program is generated, but we have to understand exactly what is generated, how is it working, how is it doing this. And then that allows us to focus on optimization. A lot of what I heard over and over through these things was not about how to create content in the test program. It's how to validate that the content is good. It's how to optimize that content for cost, how to optimize that content for quality. And we need to get past this point where we spend our life creating that content, integrating that content, getting the data for that content, and then like 3 weeks after we get a new set of patterns, we actually then summarize the results. We need to get those real-time insights and actually even allow an agnostic AI engine to create new patterns based on, you know, an orchestrator. In other words, I want to target this, create the patterns and run them, and it'll go off, create those patterns to target those specific failure modes, get them on the tester, capture the data, and drive it back into the system so that that loop eventually tries to converge. And most importantly, this drives to just faster time to market. So if we can get real-time insights offline, real-time insights online, and drive this into how do we think about what am I working on and how am I working on that data to basically get to the insights. So for me, you know, thinking back in time and thinking over the next 10 years, it's not if this is going to happen, it's just how quickly. And I think of how I started in this industry and about how exciting I felt, you know, the first time I sat down at New Silicon and started working on it and started seeing waveforms and seeing, you know, cause and effect. You know, the same thing is going to happen. It's just going to happen in this different way. And as you start understanding these critical insights, we can start thinking about out of the box as to how do we solve these problems, where now we can really focus on the problem. So with that, I'm open to any questions or comments on my material.
Thanks, Rick, for very interesting and nice presentation. We have time for questions, and we have some micros in the room. If somebody wants to ask a question, can just go to the micro, and I will break the ice with the first question. Partly you answered, I was thinking about the number of people involved in test development and so on. So I was thinking, starting from 1, then 5, then 10, every 15, 20 years. And with the AI, most probably this is going to be getting a little more flat curve. But how about the expectation to have more AI people, data scientists instead of test engineers, so probably there will be a need for people who knows more about AI, how to use AI, and less about testing. Mm-hmm. Is that good, or there would be some drawbacks? What your opinion about that?
I think I mean, I've heard, depending on the company, whether it's, Microsoft or some of the bigger companies that have a fundamental software ecosystem as part of their DNA, they basically saw very early on that, they needed like 3 software engineers for every 1 test engineer so that the test engineer could focus on test with a known good sort of test program creation process. So I think it's good that the test engineers can actually focus on the test. And actually what we see in the discussions and panels, you don't hear a lot of discussion about the ATE. You don't hear a lot about the production sort of environment at the ITC level. You learn more about how do we create patterns, how do we compress patterns, how do we do this. So my expectation is that we'll get to the point where test engineers can go back to like really focusing on test and away from the software portion of the test program. And I've got some colleagues in the audience here that are amazing test engineers, and they're horrible coders, absolute terrible. And that's fine in 2025 and beyond. And in the past, I had to like tell them, stop writing code, just tell me what you want to do, and then we'll get it done. But I think if we can do that, actually Sam Altman earlier this week for OpenAI said that his coders don't code anymore, they just yell at the LLMs. And so he's basically stopped coding, and I think Professor Lee also said that he doesn't allow his engineers anymore to write Python. They have to generate Python. And so I think this is good for test engineers to go back to what our core competency was, which was test, and abstract us away from these distractions of software, you could say.
Thank you very much. We have time for more questions. Very quiet audience today. We have one. Please state your name and affiliation.
Hello, I'm Nigel Gray. I'm a test engineer over at Medtronic. I was curious, we're a highly regulated space, and I was curious how you have integrated your ecosystem into kind of a highly regulated space, if that applies.
Yeah, so for automotive, and we look at the requirements-driven design flow, the concepts that we're driving to were really sort of at that archive state, where in like Copilot, you can ask it to like summarize, the conversation that I've had with you over the last, 24 hours. And it'll output the context associated with that so that if you want to throw that into another LLM, you can do that. And so in this regression flow, the key thing that we're looking at there is how do we create like a fingerprint of that test solution that was created at that instance time. And then also like from the universal test spec, and from that, it's like we have all the traceability up there, and then we have the output traceability. So we're using the same fundamental principles that we've used in terms of traceability, alignment, trackability, and that's why I also like the advanced revision control, pattern management. All of these things are super critical. So again, we control the inputs very regulate with high levels of regulation, and we track the outputs with a high level of regulation and analysis. And it's really in the middle there where we don't get into trouble. And that's where a lot of the, call it, productivity occurs. Does that answer your question? Okay.
Hello, I'm Mark Roos of Roos Instruments. The AIs we have today are all trained on historical information, knowledge that we've generated in the past with this somewhat inefficient, as you say, approach of test engineers programming. As we go forward with new technologies and nodes, how do you expect to generate the training material that these non-experts are going to benefit from?
We'll just ask AI to do it. So training is an interesting thing, and we've approached this a lot of different ways. Like with the tooling associated with the AI, we have a whole section with regards to like 1-minute videos and clips that basically walk people through things. And the other thing is we have, call it use groups, that are under a microscope with regards to how are they using the tooling, how is the tooling working for them, you know, what are the results? And from that, and then also the test engineering framework group, which helped me a lot with this presentation and being a sounding board, is it's a central group that allows them to focus on how the tooling fits together, how the ecosystem is generated, how all these things fit together. And then the subject matter expertise that comes out of the tooling is then falls onto the subject matter experts. And again, generating that feedback loop that basically says, you know, if it gave me some wrong information, having an AI team or a central team that allows us to then fine-tune that response or figure out what the source of that hallucination is.
So this is a high mic. I definitely appreciated the ecosystem view and the continuity between all the different domains that have to operate closely together. Can you talk about how you're using data and how you can maximize the data analytics to better inform design, like leverage process learning, you know, based on the framework that you're putting in place? How are you leveraging that to introduce design optimizations and make better decisions earlier in the process?
Yeah, so something that rang true with me during one of the talks yesterday was just design can never tell us how many patterns there are going to be. And once they tape out, then they tell us how many patterns there's going to be. And I've always struggled with monetization of test as it's associated to circuits. And so one of the things from a design perspective that I'm really looking at is grabbing critical attributes of the design and tying them directly to the physical attributes of the test. And then creating benchmarks that allow that to be more like a defect density curve or something similar that allows us to look at things like test efficiency. Like I'm spending 1 second on a SAR ADC test on this technology, but I'm spending 100 milliseconds on the same specs, the same this, the same that, in another chip. And these design level views or these vertical views should allow us to basically say from a test time perspective, you know, how much test time is spent on this area of silicon at this technology node. And start us to be, instead of talking about pattern count, you know, we can tie that more directly to like gate count. Or when I look at analog circuits, we have all been there where an analog circuit can be super easy to test or super difficult to test. You know, Steven Sunters spoke a lot about having a deterministic stuck at analog test versus a parametric analog test. And so I think by having this data such that we can monetize the exact time and compare, call it apples to apples, we can then more quantifiably challenge design engineering to grow their circuit a little bit to make it testable, to do things that allow us to drive this into the design phase. And today I don't have the ammunition at my fingertips to drive these initiatives with the right level of force, you could say. And so that's really how I look at how this data, and we did this to a certain degree already with our platform designs, but it's very ad hoc in how it was done because we didn't have this sort of data lake approach. Okay? Thanks.
Then, once more, thanks, Rick, for your very nice presentation. We have a certificate of appreciation for you.
Thank you. Thank you very much. Thank you.
So a few more information before we can enjoy the exhibit open. About next year, more information will be given at the closing session, but take some notes. For paper submission next year, we will have March as time frame deadline and notification in June. Right, that should be almost all. Now exhibit opens, and yeah, enjoy the conference. Thank you very much.